let's get started. The plan for today is to finish up the variational autoencoder model. And so we'll talk about the ELBO again. We'll see how we can actually solve the corresponding optimization problem. And then we'll actually explain why this model is called the variational autoencoder. And so we'll show some connections with the autoencoders we've seen in the previous lectures. And we'll see how it generalizes them. And you can think of it as a way of turning an autoencoder into a generative model. So as a recap, recall that we're talking about a kind of generative model called the variational autoencoder, often denoted VAE for short. In the simplest form, you can think of it as something like this. It's a generative model where you first sample a simple latent variable z, for example, by just drawing from a multivariate Gaussian distribution with mean zero and covariance the identity matrix, kind of like the simplest distribution you can think of. And then what you do is you pass this sample that you obtain, this random variable z, through two neural networks, mu theta and sigma theta, and these two neural networks will give you the parameters of another Gaussian distribution. So they will give you a mean vector and a covariance matrix, which will depend on z. And then you actually generate a data point by sampling from this conditional distribution, p of x given z. And as we've seen, the nice thing about this kind of models is that even though the building blocks are very simple, like you have a simple Gaussian prior p of z, and you have a simple conditional distribution p of x given z, which is again just a Gaussian. The marginal distribution over x that you get is potentially very flexible, very general, because you can kind of think of it as a mixture of a very large and infinite number of Gaussian distributions, right? For every z, there is a corresponding Gaussian. You have an infinite number of z's, so you have an infinite number of Gaussians that you're kind of like mixing. So if you want to figure out what was the probability of generating a data point x, you would have to integrate over all possible values of the latent variables, and you would have to see what was the probability that that latent variable would give me this data point, and that kind of like gives you a lot of flexibility. And as we've seen, kind of like the nice thing about this is that it gives you a very flexible marginal distribution over x, and it kind of like also gives you a way to do unsupervised learning, in the sense that you can try to infer z given x, and hopefully you might discover some structure, some latent factors of variation that can describe a lot of the variability that you see in the data. So it can be used for unsupervised learning. You can kind of think of it as an extension of k-means, where the latent variables are more flexible and they can discover more complicated factors of variation. What we've seen is that there is no free lunch, in the sense that the price you pay is that these models are more difficult to train. And at the end of the day, it boils down to the fact that evaluating likelihoods is expensive, it's difficult. So evaluating p of x is expensive because you have to essentially check all the possible values of z that could have generated that data point x. And what this means is that you cannot evaluate likelihoods of data points, or you can do it, but it's very expensive. And therefore, training is also very hard, because there is not an obvious way to just optimize the parameters to maximize the probability of a particular data set that you have access to, because computing likelihoods is hard. And this is different from autoregressive models, where, on the other hand, it was trivial to evaluate likelihoods because you just multiply together a bunch of conditionals. Question?
A quick question. Can we parameterize p of z itself, or is that, do we have to have?
Good question, yeah. So the question is whether we can, p of z could be learned, essentially, or does it have to be something fixed? It can be learned. This is kind of like the simplest setup that is already powerful enough to do interesting things. Z is fixed, but as we'll see when you go through the math, nothing really stops you from using a more complex prior distribution over z. And it could be something that you can learn. For example, you could use, the simplest thing would be the parameters of that Gaussian are learned. So instead of using a mean zero and a fixed covariance, the identity matrix, you could learn those parameters, or you could use an autoregressive model for Z. Or what you could do is you could stack another autoencoder, another VAE, and then you can have kind of like a hierarchical VAE where the Z is generated from another variational autoencoder. And that's kind of like a hierarchical VAE, and it's essentially what's going to be a diffusion model. If you stack this many, many times, you get a more powerful model. But this is kind of like the simplest, interesting model that highlights kind of like the challenges, and it's already useful in practice.
What makes more sense, stacking multiple VAEs on top of each other, or just increasing the number of layers of these two neural networks that you define?
Yeah, so good question. So the question is what's the difference between kind of like increasing the dimensionality of Z or adding multiple layers versus kind of like increasing the depth of the neural networks that give you the mapping from Z to X. And the behavior of those two things, both of them would give you more flexibility, but the behavior is kind of like very different, because you can make this network as deep as you want, but sort of like P of X given Z is still a Gaussian. And so that kind of like restricts what you can do, as will become clear later when we talk about the training. I mean, that increases the flexibility to some extent, but it's not the same as adding more kind of like mixture components, which is kind of like what you would get if you were to either stacking another VAE or maybe using a more increasing the dimensionality of Z. So both of them go in the same direction, but they do it in a different way. Cool. So that's the no free lunch part, and basically what we've seen, we started looking into ways to train these kind of models, and as we'll see, the way to train this kind of like latent variable models relies on this technique called variational inference, where we're essentially going to have an auxiliary model that we're going to use to try to infer the latent variables. And in this course, this auxiliary model is also going to be a neural network. It's all going to be deep. Basically, you're going to jointly train the generative model and an auxiliary inference model that you're going to use to try to reduce the problem to the one that we've seen before, where both the X and the Z part is observed. And that's kind of like the high-level idea. And it builds on that result that we've seen in the last lecture of building an evidence lower bound, right? So we've seen that we can obtain a lower bound through Jensen's inequality, basically, on this quantity that we would like to optimize by essentially using this kind of auxiliary proposal distribution Q to try to infer the values of the latent variables. Remember, the challenge is that you only get to see X, you don't get to see the Z part, so you have to infer the Z part somehow. The ELBO trick essentially uses a distribution Q to try to infer the values of the Z variables when you get to when only the X is observed, and it constructs that kind of lower bound on the marginal likelihood, the quantity on the left, the one you would like to optimize as a function of theta. And what you can do is you can further decompose that objective into two pieces. You have a first piece, which is basically just the average log probability when both the X part and the Z part are observed, when you infer the Z part using this Q model. So kind of like the first piece looks a lot like the setting we've seen before, where everything is observed, both the X and the Z part are observed. The only difference is that you are essentially inferring the latent part using this Q model. And then there is another piece which does not depend on your generative model. It does not depend on P at all. It's only a function of Q, and it's basically saying it's the expected value under Q of log Q, which is what we've called in previous lectures the entropy of Q. And essentially, it's a quantity that tells you how random Q is, how uncertain you should be about what is the outcome of drawing a sample from Q. And we see that basically this elbow has these two pieces. There is a term that depends on the entropy of Q, and there is a term that depends on the average log probability when you guess the missing parts of the data using this Q distribution. And so the higher the sum of these two values, these two terms is, the closer you get to the evidence, to the true value of the marginal likelihood. And what we've sort of briefly discussed in the last lecture is that if you were to choose Q, this inequality holds for any choice of Q. If you were to choose Q to be the posterior distribution of Z given X under your generative model, then this inequality becomes an equality, so there is no longer an approximation involved, and the evidence lower bound becomes exactly equal to the marginal likelihood. And as an aside, this is exactly the quantity you would compute in the E step of the EM algorithm, if you've seen it before. This kind of procedure has the flavor of an EM algorithm where you have a way of kind of like filling in the missing values using this Q distribution, and then you kind of like pretend that all the data is fully observed, which is kind of like this piece here, and then you have this entropy term. But there's a connection between this kind of like learning methods, EM, and variational learning, that what we're going to talk about today. They both kind of like try to address the same problem, learning models when you have missing data. EM is not scalable, doesn't quite work in the context of deep generative models, but these two methods are closely related, and that's why you can see that the optimal choice of Q would be the conditional distribution of the latent variables given the Z variables latents given X. And now, how do you see this? Well, to derive it, you can work out this expression. If you work out the KL divergence between this Q distribution and this optimal way of inferring the latent variables, which is the conditional distribution of Z given X, it's not too hard to see that if you do a little bit of algebra, this expression is equal to what you see here on the right. So we see several pieces. We have the marginal probability of X, the log probability of X, the marginal likelihood, the thing we care about. We have the entropy of Q here, and then we have this average log joint probability over a fully observed kind of data point. The same pieces we had before. And the kind of like key takeaway is that KL divergence we know is non-negative. For any choice of Q, the left-hand side, this KL divergence has to be non-negative. And so now if you rearrange these terms, we re-derived the elbow in a slightly different way. And you see, like, if you move this entropy of Q and the first term here on the right-hand side, you get, once again, the elbow. You get that the log marginal probability of a data point is lower bounded by the same expression that we had before. So this is another derivation of the elbow that just leverages the non-negativity of KL divergence. This derivation is nicer because it actually shows you, how loose or how tight this lower bound is. So you can clearly see that if you choose Q to be the conditional distribution of Z given X, so this bound holds for any choice of Q. If you choose this particular distribution, then this KL divergence has to be 0, because it's, the left and the right argument of that KL divergence are the same distribution. And so this inequality here becomes an equality, and so we get this result that sort of like the elbow is tight, so it exactly matches the log marginal probability when you basically infer the latent variables, the missing variables, using this optimal proposal distribution that uses the true conditional probability of Z given X to guess the parts of the data that you don't know. Yeah.
Is it like, so my understanding is that we want to do this QFX because if we just do Monte Carlo, it's too sparse. So since this will give us the maximum likelihood we can do this. Can we actually do this, and how easy is it to compute P of C?
Yeah, great question. So, I mean, I guess we said that, yeah, we cannot really evaluate this because it's too expensive. Now it seems like maybe we can do it if we were able to choose the optimal Q. This is more aspirational. We're not going to be able to actually make this choice. But it's kind of like showing us that we should try to pick a Q that is as close as possible to the optimal one. And although in practice, for something like a variational autoencoder, as we will see soon, this object here is too expensive to compute. Like if you were able to compute the posterior, then you would also be able to essentially compute the quantity on the left that we want to optimize. And that will motivate the whole idea of variational inference, which is basically saying, let's try to optimize over Q to try to find the tightest possible lower bound. So we're going to have a separate kind of like neural network that will play the role of Q, and we will jointly optimize both P and Q to try to maximize this evidence lower bound. And one of the components will be the decoder in the VAE, which is P. The other component will be the encoder of the VAE, and that's going to be Q. And they will have to work together to essentially try to maximize the elbow as much as possible. And you can see from kind of like this expression that the optimal encoder, the optimal Q, would be the true conditional distribution of Z given X. So it's kind of like inverting the encoder. So again, it sort of starts to have the flavor of an autoencoder, where there is a decoder model, which is the P of Z given X, with the P of X given Z. And then there is an encoder, which is kind of like trying to invert what the decoder does, because it's trying to compute the conditional of Z given X. Hopefully it will become clearer later, but essentially this confirms our intuition that we're looking for likely completions. So given the evidence, given X, we're trying to find possible completions, values of the Z variables that are consistent with what we see, where the consistency is determined by this joint probability P of Z comma X, which is essentially the generative model. It's the combination of the simple prior and then the other neural network that will map it to parameters of a Gaussian, and then you sample from it, which is just the P of X given Z. So now the problem, as kind of like was already brought up earlier, is that this posterior distribution in general is going to be tricky we cannot actually compute it. And in some of the toy models that you might have done EM with, for example, sometimes you can compute it. Like if you have a mixture of Gaussians, you can actually compute this analytically. That's why you can do the E step in EM. But in many cases, doing that E step is intractable, right? So if you think about the VAE, essentially what you're doing is you're trying to invert the decoder. So recall that in a VAE, the conditional distribution of X given Z is given by this, it's relatively simple, it's a Gaussian, but the parameters of the Gaussian depend on these two neural networks, mu and sigma. And so what are you doing when you're trying to compute P of Z given X? You're basically trying to invert these neural networks. You're given X, and you're trying to find which Z's were likely to have produced this X value that I'm seeing, which is potentially pretty tricky because you have to understand how the neural network maps Z's to outputs, and you kind of like have to invert a neural network in a probabilistic sense. Does this make sense? Cool. And so the idea of the way we're going to train, again, this variational autoencoder is we're going to try to approximate this intractable posterior. Like we know that would be the optimal way to infer the latent variables given the observed ones. So we would have to invert these two neural networks. We would have to invert this conditional, this decoder. In general, that's going to be tricky. And so instead, we're going to define a family of distributions over the latent variables, which are also going to be parameterized by some through a set of parameters phi, the variational parameters. And then we're going to try to jointly optimize both the Q and the P to maximize the elbow.
Can you explain again why we want to even be able to compute the posterior z given x if our goal is just x or like x given z?
Yeah, so the reason we might want to get this posterior distribution is that, as we've seen here, if you were to use Q here, this elbow would be tight, so there would be no approximation. And by optimizing the right-hand side, you would actually be optimizing the left-hand side, which is what we want. This is a little bit of a chicken and egg problem, though, because if you think about it, how is P of z given x defined? It's the joint P of x comma z divided by P of x. And P of x is what we want, right? So that's why sort of like it's chicken and egg. You can't really compute this thing, and if you could compute this thing, then you would know how to get the left-hand side, so you don't even need to do the elbow computation at all. But this is giving you a recipe to get a lower bound that holds for any choice of Q, and the game is going to be, let's try to find something that is as close as possible. Let's try to find something tractable that can get us as close as we can to what we know would be the optimal solution. And that will end up being tractable.
Quick question about notation. What does variational parameters mean? Do you mean that by like parameters of a neural network or something?
Yeah, so let's see what that means. For example, Q could be a family of Gaussian distributions where phi denotes the mean and the covariance. So it could be something like this. Maybe you have one part of phi denotes the mean of the Gaussian, the other part denotes the covariance, and somehow you are trying to pick a good choice of these two parameters to get as close as possible to the true posterior that we know we would like to get for doing this to compute the elbow. And that's basically what variational inference is going to do. It's going to reduce this to an optimization problem where we're going to try to optimize these variational parameters to try to make this distribution Q as close as possible to this intractable optimal choice that we know exists, but we don't know how to compute. So in pictures, it might be something like this. There is a true conditional distribution, P of z given x, which is, for simplicity, it's shown as a kind of like a mixture of two Gaussians in blue here. And let's say that you're trying to approximate that distribution using a Gaussian. Then what you can do is you can change the mean and the variance of these Gaussian distributions to try to get as close as possible to the blue curve. So for example, you could choose the mean to be 2 and the variance to be 2, which would be two choices of phi 1 and phi 2, and maybe that would give you this orange curve. And if you could choose what's the best approximation here, would you choose the orange curve? Would you choose the green curve corresponding to a mean at -4 and a standard deviation of 0.75? I guess what it looks like is that the orange curve is better because it's kind of like roughly has the shape of the distribution we want. It's not quite the true posterior distribution, but it's pretty close. And so if we somehow are able to come up with this variational approximation, with this simple distribution that is roughly close to what we want, that might be good enough for learning. That's kind of like the idea behind variational inference. Let's try to optimize this distribution Q over these variational parameters phi to try to make this Gaussian distribution as close as possible to this object that we know is there, that we know we would like to approximate as well as we can, but is often intractable.
Can you clarify the dimensions of the latent variables and the data? So are they generally not the same dimensions?
Yeah, so the latent variables don't necessarily have the same dimensions as the data. And this for this, the only thing that matters are the latent variables. We're just trying to find a distribution over the latent variables that is as close as possible to the true posterior distribution.
So normally, like we will choose like a simple latents, right?
Yes. So again, in practice, in a variational autoencoder, this Q will actually be again a Gaussian. So everything will be relatively simple. That will come up soon, but essentially, even in a variational autoencoder, what you would do is you would try to optimize these parameters phi to try to match the true posterior distribution, the true P of z given x as well as you can. Yeah.
How would you evaluate Q?
Yeah, how we evaluate Q? The natural thing to do would be to look at KL divergence, right? We know KL divergence is telling you how far off your elbow is from the true thing. And so it might make sense to try to choose a Q that is as close to P of z given x in KL divergence. And that might be, that's kind of like what's going to happen when we do, when we optimize the elbow and when we basically train a variational autoencoder. All right, so that's sort of like the idea, and in pictures again, it looks something like this. Like for a given x and a given choice of theta, which are the parameters of your variational autoencoder, your decoder, there is a true value of the log probability of x, which is kind of like this blue line here. And then you can imagine that if you have a family of distributions Q, which are parameterized by phi, as you change phi, you get lower bounds that could be tighter or looser, depending on how close, depending on this KL divergence value, how close your distribution Q is to the true posterior. And so essentially what we're going to do is we're going to define an evidence lower bound, which not only depends on Q, that not only depends on theta, which are the parameters of the generative model, but also depends on this choice of variational parameters phi. And what we're going to do is we're going to try to jointly optimize this right-hand side over theta and phi, so that by optimizing theta, we try to make this lower bound as close as possible to the thing we care about. And by optimizing theta, we are pushing up a lower bound on the marginal likelihood, which is again a surrogate to the maximum likelihood objective. And so it kind of like makes sense to jointly optimize this elbow as a function of both theta and phi. So what we had here was one kind of like lower bound, which holds for some choice of Q. And now we're saying we're going to define a family of lower bounds that are going to be indexed by phi, these variational parameters, and we're going to try to find the choice of phi that kind of like makes the lower bound as tight as possible. Because that means that we get the best approximation to the quantity we care about, which is the likelihood of a data point. And that's basically the way you train a variational autoencoder. You jointly optimize this expression as a function of theta and phi. And it will turn out that there's basically going to be two neural networks, a decoder and an encoder. The decoder is basically theta, the encoder is going to be the phi, and these two things work together to try to maximize that evidence lower bound. And we know that, again, sort of like the gap between the elbow and the true marginal likelihood is given by this KL divergence. And so the better we can approximate the true conditional distribution of z given x, the tighter the bound becomes. So that's basically going to be the objective, back to your question. Kind of like by pushing up this quantity as a function of theta and phi, we're implicitly trying to reduce the KL divergence between the proposal distribution that we have, which is this Q, and the true optimal one that would require you to invert the neural networks exactly, that we don't know how to do But we know that how far off we are with respect to the scale divergence, or how big the scale divergence is, determines how much slack there is between the lower bound and the blue curve. And so you can think of the E step of EM as kind of like giving you the tightest possible lower bound. And that's why you do it as the first thing in EM, is to compute the true conditional distribution, because that gives you the tightest possible lower bound. So we can no longer do it here because we cannot compute the tightest possible lower bound, but we can try to get as close as we can. Yeah.
Just so that I'm understanding correctly, we're trying to compute log p so that we can do maximum likelihood estimation.
Yeah.
Right? Okay, so there are two optimization objectives here, right? So the first one is we're trying to maximize log p, and the other one is we're trying to maximize the elbow to get close to p as possible.
Yeah.
Am I understanding correctly?
Sort of. So the dream would be to just optimize log p, this quantity on the left-hand side, as a function of theta. That, if you could do that, then that's just like training an autoregressive model. That's the best thing we can do. That quantity, we don't know how to evaluate, but we can get a bound that holds for any choice of phi, which is kind of like the red curve shown here. And so what you could do is you could try to jointly optimize over phi and theta to get a pretty good surrogate of what we would like to optimize. We are going to optimize the lower bound instead, and at the same time, we're going to try to make you are optimizing a family of lower bounds, and we're trying to find the tightest possible bound and increase that bound as a function of the theta parameters of your generative model to maximize the likelihood of a data set. Exactly.
If you were to like run this on inference, quote unquote, so you'll just basically throw out Q and just like worry about like the P.
Yeah. So the question is, at the inference time, do you need Q? If you just want to generate, you don't need Q. If you just want to generate, you have your optimal choice of theta that perhaps you obtain by optimizing the ELBO. And all you need is that, right? You can sample Z, you feed it through your decoder, your two neural networks, mu theta and sigma theta, produce a sample. Now, if you wanted to evaluate the likelihood of a data point, because maybe you want to do anomaly detection or something like that, then you might still need the Q, because that sort of like helps you compute this quantity. Like, at least it gives you a bound, and to the extent that the bound is good, you might need that. And so Q is still useful, but if you just care about generation, you are right, you can throw it away after you've trained the model.
Isn't KO divergence no negative? Shouldn't it be like a minus KO divergence to be like a lower bound?
I think it's fine, because basically L is below, right? So this one, so the log probability is always above.
So, like, actually, the phi is actually somehow related to theta, right? It's but when you do this optimization, you actually don't care about this. Like, what exactly should we think about that?
That's a great question. I mean, is phi related to theta? And the optimal phi would certainly be related, because the optimal phi would try to give you the posterior distribution with respect to theta, right? So we know that the optimal choice, actually I have it here, the optimal choice of phi would be this posterior distribution, which depends on theta. And so they are certainly coupled together. By jointly optimizing over one and the other, you are effectively trying to get as close as you can to that kind of point, but it's not guaranteed to be exactly equal. So these two things are related to each other, but the final value of phi that you obtain is not necessarily the one that gives you this, that matches the true conditional distribution. It's going to be close, hopefully, because if you've done a good job at optimizing, hopefully this KL divergence is going to be small, but there is no guarantee because perhaps the true posterior is too complicated and your Q is too simple, so you might still be far off. But there is certainly an interplay between the two in the sense that at optimality, this KL divergence should be zero, and so they should match each. Cool. So that's basically how you train a variational autoencoder. You jointly optimize that expression here as a function of theta and phi. Now, and again, this is kind of like the picture. It's a little bit tricky because there are two optimization problems that happen at the same time. But what happens is that there is these theta parameters, which are the parameters of the decoder, the thing that you would really like to optimize. And for different choices of thetas, there is going to be different likelihoods that are assigned to the data. And I'm showing this curve here, this black solid curve as being the true marginal likelihood. If you could, you should just optimize that as a function of theta. That would be maximum likelihood learning. That would be great. The problem is that we cannot quite compute that thing. And so we're going to settle for lower bounds, which you see here, meaning that these are curves that are always below the black curve. And there is a family of lower bounds. There's going to be many lower bounds. Any value of phi will give you a valid lower bound. And what we're going to try to do is we're going to try to find a good lower bound, meaning that one that is as high as possible, that is as close as possible to the black line. So there's going to be a joint optimization over theta, which is what tries to maximize the probability of the data set. But we're going to achieve that by optimizing a bound, let's say optimizing the red curve or optimizing the orange curve, and at the same time trying to pick a bound, so I'll pick a choice of phi that gets us as close as possible to the black line.
If our goal is to fit the black line as well as possible, why are we constraining ourselves to a normal distribution? Would it not be maybe possible to learn aspects of the distribution as well?
Which part is it, you think is the normal in the conditional or the prior? Or the Q?
I'm talking about Q.
Q, yes, great question. So the more flexible Q is, so if instead of using just a Gaussian, maybe use a mixture of Gaussians, maybe use an autoregressive model, the better this bound becomes. And so the better you're going to do at fitting your original decoder. So there's many papers where people basically propose better choices for Q, which essentially means more flexible families, and that can give you a better data fit by basically making this proposal distribution more flexible. So indeed, that's a great way to make the model better, make Q more expressive, more flexible.
Like, let's you optimize over phi to fit a curve that matches the black line, but then afterwards your black line is going to change itself, right? You just keep doing that over and over again.
Yeah, so that's a great question. I mean, the thing, it seems like as you change, sort of like it goes back to the other points that were raised, that phi and theta are coupled together. So a good, sort of how good a bound is depends on or how good a phi is depends on the current choice of theta. And so if you are around here, maybe this, as you can see here, around this choice of theta, maybe the red curve would be better than the orange. But then if you have a different choice of your variational parameters, then maybe the orange curve starts to become better. And so as we jointly optimize, we'll have to keep them in sync. In practice, what we do is we just do gradient ascent on both theta and phi. So we try to keep them. But you could also just keep theta fixed, optimize as a function of phi as well as you can. That gives you the tightest bound, and then optimize theta by a little bit. That is actually what happens in EM. You can think of EM as giving you the tightest possible bound for the current choice of theta. And then in the M step, you optimize the lower bound as well as you can. Here, we're not going to do that. We're going to do gradient-based updates, but it's the same kind of philosophy, trying to jointly optimize one and the other. Cool. So, all right, so let's see how we do that. So we know that for any choice of Q, we get that lower bound. That's the elbow. Now, what we would like to do, recall, is that we have a data set, and we would like to optimize the average log probability assigned to all the data points in the data set. So we don't just care about a single x, we care about all the x's in our data set D. And what we can do is, well, we know how to bound the log probability for any x and any theta through the elbow. And so we can get a lower bound to the quantity on the left, which is the average log likelihood assigned to the data set, by just taking the sum of the elbows on each data point. Right, so this is the elbow for a general x. We can get the elbow for each data point, and we get this expression. Now, the main complication here is that we're going to need different queues for different data points. And so if you think about it, the posterior distribution, even for a same choice of theta, is going to be different across different data points. And so you might want to choose different variational parameters for different data points. And so you don't have a single set of variational parameters, phi, but you have a single choice of theta because you have a single generative model for the whole data set. But then at least if you do things this way, you would need to choose variational parameters differently for different data points. I mean, we'll say that this is not going to be scalable, but this would be and so we'll have to introduce additional approximations to make things more scalable, but this would be the most natural thing to do. For every data point, you try to find the best approximation to the posterior for that particular choice of xi, and then you jointly optimize the whole thing. You try to make the lower bound for each data point as tight as possible so that the sum of the lower bounds is going to be as good of an approximation as you can to the true quantity you'd like to optimize, which is the true marginal likelihood here.
Why do you need a separate for each ratio?
Yeah, I think I have an example here. So that now in this example, let's say that the latent variables are the pixels in an image. So then at least they are meaningful and you can kind of like get a sense of what the posterior should be. So let's say that we have a distribution over images, and the x variables are the bottom half of the image, and the z variables are the top half of the image. But let's pretend that maybe you're fitting an autoregressive model, but we are in this kind of like situation where some of the images some parts of the image is missing. So you never get to see the top half of the image. So that's a latent variable. So it's no longer a VAE, it's a slightly different model, but it's just to give you the intuition of what we're trying to do here. So to fit your autoregressive model, your transformer model, or your RNN or whatever, you need to somehow guess the top half of the image if you want to evaluate this joint probability, and you can optimize your parameters. And one way to do it is to basically use this variational trick of trying to guess the values of the missing pixels, and then pretend that you have a fully observed data set, and then just optimize. But there is different ways of guessing the missing values, the missing pixels, right? So you can define a family of distributions over the missing pixels. And here, just for simplicity, I'm saying, okay, the pixels are just binary 0, 1. And so you have a bunch of variational parameters that will basically tell you the probability that you should choose each individual pixel that is not observed to be on or off. And so in this case, you have one variational parameter per missing pixel. And you can kind of see that what's a good approximation depends on the bottom half of the image. Like if you get to see this part, would you choose phi I 0.5 as your approximation of the posterior? Which basically means the way you're going to guess the missing values is by randomly flipping a coin on each location. It's probably not a good approximation to the true posterior. You kind of know that this is probably kind of like a 9, and so you kind of like want to guess that way. And so probably not a good one. Would turning everything on be a good approximation? Probably not. Again, you sort of like want to choose, turn on the pixels that correspond to the 9. But you see that it depends on what you see. It depends on the evidence X. So if you see this, you might say it's a 9, but if you see a straight line, then maybe you think, oh, it's a 1. And so you want to choose different values of these variational parameters. And so even though theta is common across the data points, the values of the latent variables that you infer should be different. Again, going back to the variational autoencoder, if Z now captures latent factors of variation like the class of the data point or whatever, again, you'd like to make different choices for how you infer Z depending on what you see, depending on the X part. And so that motivates this choice of, okay, we want to optimize, we want to choose different phi's for the data points because the latent variables are going to be potentially very different across the different data points. Or another way to say it is that if you think about the generative procedure of the VAE, you're generating these X's by feeding random noise essentially into a neural network. And depending on the X you see, you might want to make very different guesses about what was the random noise that you've put through your decoder, through your neural network. And so you want to choose different choices of phi's for the different X's that you have in your data set.
I don't know if you've covered this already, but does maximizing the right elbow guarantee that it also maximizes the left, or could it be also kind of like maximize that, but it actually might be really optimal?
Yeah, so that's a great question. To what extent is optimizing the right-hand side a good approximation to optimizing the left-hand side? And it's a reasonable approximation in the sense that you know that whatever value you have here, the true thing can only be better than what you got. You could be far off, and in fact, you could be doing weird things where maybe by, maybe let's see whether I have it here, but it could be that it looks like you're optimizing, the lower bound goes up, but the true thing actually goes down. Like you could imagine a shape here where, let's see if I have an example here, but basically it looks like, maybe if you go from here to here, like it looks like the red line goes up, but the black line might actually go down. So in that sense, there is no guarantee because the bounds could be very far off from the true thing. But what you know is that the true objective function is going to be at least as good as what you get by optimizing these, which is not a bad guarantee to have. All right, so now this is how to choose them. Now, how do we actually do this? The simplest version would be to just do gradient ascent on this objective function, right? The elbow, if you expand it, would look like this. So for every data point xi, you would have this expectation with respect to this variational distribution Q, this way of inferring the latent variables given the observed ones, and then you would have the log probability and basically in the fully observed case, and then you have this term, which is kind of like the entropy of Q. And so what you could do is you could initialize all the optimization variables somehow, and then you could randomly sample a data point, and then you could try to optimize this quantity as well as you can as a function of the variational parameters. So you compute a gradient of the quantity with respect to the variational parameters. You try to make that elbow as tight as possible for the ith data point. And then until you can no longer improve, you find some kind of a local optimal. And then you can take a step on the theta parameters. So your actual decoder, the actual VAE model that you use for generating data, given the best possible lower bound. So this inner loop will find you the best lower bound. This step 4 will take a step on that optimal lower bound.
Why do you get rid of the H going from line 1 to 2?
I'm just expanding it. So the H is the entropy, which is the expected log probability under Q. This is not quite going to be the way we're going to train a variational autoencoder. It turns out that it's actually better to sort of like keep theta and phi in sync, but you can kind of imagine that a strategy like this could actually work as an optimization objective.
Is it like how computationally efficient is it going to be? It seems like each kind of optimization step is going to take a lot of iteration.
Yeah, so how efficient it is? Well, first of all, we'll see that the first challenge is to figure out even how to compute these gradients. These gradients are going to be not too expensive, luckily, as we'll see. But there is a question of, should you take more steps on phi, less steps on theta? Should you do one step on theta, one on phi? There is many strategies that you can use, and it's not even known actually what's the best one. This is one that is reasonable. It's more like a coordinate ascent procedure. You find the best theta, and then you optimize. You find the optimal phi, and then you optimize theta a little bit.
So the reason why I understand we need we need parameters per data point is because in the real distribution, like the best lower bound is by actually factoring it on x or z given x. So and over here, since we're not seeing x, we need one for each point, but can't we like parameterize q of z also on x?
Yeah. So that's going to be the way we're going to make things more scalable. It's called amortized inference. It's going to be how we move from this vanilla version to something that is going to be worse from the perspective of the bound you get, but it's going to be more scalable because there is not going to be one optimization parameter per data point. We're basically going to do exactly what you suggested. We're going to kind of tie together. We're going to have a single queue that is supposed to work well across different x's. There is going to be a neural network that will essentially try to guess this phi I star as a function of x. And that's, sort of like, I think it's better to understand it through the lenses of, okay, first you optimize and then you try to approximate it, but that's going to be how a VAE is actually trained. There's basically going to be a separate neural network that will take xi as an input and will produce a guess for this phi I star, the optimal choice of variational parameters for that data point as an output, and that's going to be the encoder of the VAE.
So, as you said, we can use a neural network to guess the I, right? The phi I. But so without using neural network, like what kind of how would we choose as the?
So without a neural network, you can do this. Like it's just going to be it's actually going to work better than whatever you can get with the neural network because you're optimizing over.
Right.
You have less constraints, right? Kind of like what was said before about let's make Q more as expressive as possible. This is going to be better, but it's just going to be slower and not going to be scalable. But if you can afford to do this, this is going to be better, basically.
You said that previously, like a good choice of phi I would probably be like the top half, close to the top half pixels of number 9 or something. But if we don't choose the phi I's carefully, are we going to get stuck into local optimum and where you will just not get out of it? Is it what's going to happen?
Yeah, that's a problem. Yeah, because here we're sort of like jointly optimizing these two and hoping that we can find something. But you can imagine, sort of like if the choice of phi is really bad. Initially, at least, it's probably going to be random or something, and so you're going to be doing a very bad job at guessing the latent variables, and so you might not be able to actually optimize the theta, and so you might get stuck into a very bad sort of like local optimum. And this is non-convex, so you have no guarantee in terms of like being able to find a good solution for this optimization problem. And so those issues indeed. We have them here, and you have to sort of like hope that gradient ascent will find you a good solution, but you could certainly get stuck. Cool. So that's sort of like conceptually at least, a good way to think about how you would train a model like this. And the kind of part that is still not obvious is how you compute these gradients. How do you compute the gradients with respect to theta? So we need two gradients. We need at step 3.1, we need the gradient with respect to the variational parameters. And at step 4, we need the gradients with respect to the model, the actual decoder, the actual neural networks that define the VAE. And these are expectations for which we don't know. You cannot compute them in closed form. There is no analytic kind of like expression that you can use to compute the expectation and then the gradients off. So we have to basically rely on Monte Carlo sampling. We're going to approximate these expectations with sample averages. And so what would it look like? If you want to approximate this expectation with respect to Q, we can just do this. We can just sample a bunch of draws from Q and then approximate the expectation with a sample average. The usual trick, an expectation with respect to Q is approximately equal to the sample average if you were to sample the latent variables according to this proposal distribution Q. And as usual, the larger capital K is, the more accurate this approximation is going to be. In practice, when you train a VAE, you probably choose K equals 1, and you would just use a single sample. But in general, you could use more if you wanted more accurate estimates of the expectation. And the key assumption here is that Q has to be simple. You can't choose something very complicated because you need to be able to sample from it efficiently, and you need to be able to evaluate probabilities under Q efficiently.
When I asked the question about the Q like 10 minutes ago, you said can be something much more complex. How do they do it?
Yeah, so it has to be complex, but still it has to be a model for which you can evaluate probabilities efficiently, and you have to sample from efficiently. So a VAE, for example, would not be a good choice because you can sample from it efficiently, but you cannot evaluate probabilities efficiently. An autoregressive model would be a reasonable maybe choice because you can kind of sample efficiently and you can evaluate probabilities. What we'll see, generative adversarial networks will not be a good choice because it's easy to sample from, but you cannot evaluate probabilities. We will see something called a flow model, which is a class of generative models where you can sample from efficiently and you can evaluate probabilities efficiently. That's a good choice. That's what people actually use in practice. So those are the two constraints. Sample efficiently, evaluate probabilities efficiently. And then we want to compute gradients of this quantity, right? We want to compute gradients with respect to theta and with respect to phi. And the gradients with respect to theta are trivial because basically you can just, the gradient of the expectation is just going to be approximately equal to the gradient of the sample average, essentially. So, the gradient is just linear, you can push it inside. The Q part does not depend on theta. So the gradient with respect to theta of this part is 0. So you can basically just take your samples, evaluate the gradients of the log probability with respect to theta, and this is fully observed. So this would be exactly the same gradient as in an autoregressive model. You have the Z part, you have the X part, so you know how to evaluate these probabilities. And you just take gradients and you just update your theta parameters that way. So this part is very easy. The tricky part is the gradients with respect to phi. And the reason is that the samples you're sampling from a distribution that depends on phi. And so if you want to figure out how should I change my variational parameters phi to make this expectation as large as possible, you kind of need to be able to understand how would changing phi change where the samples land, essentially. You're sampling from this distribution, which depends on phi, and so you need to be able to understand if I were to make a small change to phi, how would my samples change? And if you take gradients with respect to theta, you don't have to worry about it because the samples, you're not sampling from a distribution that depends on theta. So you don't have to worry about how the samples themselves would change if you were to change phi. But if you're changing phi, then you need to understand how your sampling procedure here depends on phi. And so the gradient is not going to be as easy as this one. And that's essentially the problem. The problem is that you're taking an expectation with respect to a distribution that depends on phi. And so if you want to take gradients, you need to understand how the sampling process basically is affected by small changes in the variational parameters. And that's more tricky. And because we would still like to do it through some kind of like efficient Monte Carlo thing where you just sample once and then you compute some gradient through autodiff and you're done. And it's not super obvious how you would do this. And there is different ways of doing it. Later on, we'll see a technique called reinforce from reinforcement learning, because you can think of this as kind of like a reinforcement learning problem where you're sort of like, if you think of Z as being an action, you're kind of like trying to figure out your policy, you're kind of like trying to figure out how you should change your policy to perform well, where the argument of the expectation is the reward that tells you how well you're doing. And it's tricky to figure out how changing your policy affects the value that you're getting. But there are techniques for reinforcement learning that you could use. Today, we'll see a simpler, actually better way of doing things that does not work in general. It only works for certain choices of Q. For example, when Q is Gaussian, you can use this kind of trick. It's more efficient in the sense that, it has lower variance, it's a better estimator. And this technique, it's called the reparameterization trick. It only works when these latent variables Z are continuous. So it doesn't work when you have discrete latent variables. Only works when Z is continuous, like when Z is a Gaussian, for example. And so that this expectation is not a sum, but it's really an integral. So it's an integral with respect to this probability density function Q, which depends on phi, of some quantity, which I'm going to denote R because it's kind of like a reward, but R of Z is just basically the argument of the expectation. I'm just changing the notation to make it a little bit more compact, but essentially the argument doesn't matter too much. The tricky part is to figure out how to change phi so that the expectation becomes as large as possible, essentially. Right? And again, you sort of see the connection with reinforcement learning. If Z are actions, then you're trying to say, and you're randomly, you have a stochastic policy for choosing actions, and different actions have different rewards. You're asking, how should I choose actions in a stochastic way so that I get the highest possible reward? And you need to understand how changing phi changes which kind of actions you pick, which kind of Z's are more likely and less likely under your policy, which is a little bit tricky. The good thing is that if, again, Q has certain properties, for example, it's Gaussian, then there is two ways of sampling from Q. You could sample from Q directly, or you could sample from a Gaussian random variable with mean zero and covariance the identity and shift and rescale it. Right? So if you want to sample from a Gaussian with mean mu and covariance sigma square the identity, you could always achieve that by sampling from a standard normal with zero mean and identity covariance, shifting and rescaling. And what this does is that we're basically rewriting this complicated random variable Z as a deterministic transformation of something simple, of a standard and normal Gaussian random variable. This is why it's called the reparameterization trick, because we're just writing Z as a transformation, as a deterministic transformation of a fixed random variable, which does not depend on the optimization parameters. So we have some deterministic transformation, which depends on the optimization parameters, the phi parameters, that we use to transform this basic random variable epsilon, which does not depend on phi anymore. And then using this equivalence, we can compute the expectation in two ways. You can either sample from Z, sample from Q, and then evaluate R at the Z's that you get by sampling from Q. Or you can sample from epsilon, transform it through G, and evaluate R at that point. And the key thing is that now we have an expectation that no longer depends on the optimization parameters phi. Now it's an expectation with respect to epsilon, and so we can basically push the gradient inside, just like what we were doing before. Or in other words, basically we understand how changing the parameters affects the kind of samples that we get, because we're explicitly writing down the sampling procedure as a deterministic transformation of some simple fixed random variable. And so if you want to figure out how would my performance change if I were to change phi by a little bit, which is essentially the gradient, now you know exactly how your samples would change, because you have a deterministic transformation that gives you the new samples as a function of phi. And so taking the gradient of that would tell you how the samples would change by changing phi by a little bit. And so once you have this expression, or you have an expectation with respect to a quantity that no longer depends on phi, we're basically in a good shape, because we can compute this gradient with respect to phi. So here, this one would be a little bit tricky, because you have an expectation which depends on phi, and we don't know how to do this. But the expectation on the right is the kind of thing we know how to handle, because it's an expectation with respect to epsilon, which no longer depends on phi. And then we can basically push the gradient inside. Yeah?
Is R just some arbitrary function here?
R is an arbitrary function, yes. And this is something we can do by Monte Carlo, basically. All you do is you sample epsilon, and then or a bunch of epsilons, and then you approximate the expectation of the gradient with the sample average of the quantity. And basically by chain rule, you can kind of you can figure out what would be the effect of changing phi be on this expectation that you care about. Because you know that basically, yeah, just by computing this gradient, you get what you want. You know how this epsilon would be transformed, and then you know what is the corresponding reward R that you would get if you were to transform the sample in a certain way. And so you know how you should adjust your parameters to maximize the reward as much as you can. Because you know exactly how changing phi affects the sampling procedure. Yeah.
I guess I'm curious about like the continuity of the Z part requirement for this. Like, what if you had Z that was I don't know, like from like 1, 2, 3, 4, 5, 6, and then you like modeled it with a uniform distribution, and like you like either like floor it or like put a ceiling function to it. Like, wouldn't it?
Yeah, so it doesn't work for discrete random variables. If you have that kind of setting, and it doesn't even work for all continuous distributions. Like, it has to be, you have to be able to write the sampling procedure as some kind of deterministic transformation of some basic distribution that you know how to sample from. If you can do that, then this machinery, you can kind of see it goes through. But if you have something like a discrete, like categorical even random variable, then, well, it would be discontinuous, and at that point you don't know. And you can always sample it by inverting the CDF, essentially, but you would not be able to get gradients through, essentially. And so for that, you either need to use reinforce, or we'll talk about other ways to relax the optimization problem and dealing with these things. But this is only applicable to special cases like a Gaussian, which luckily is what people often use in practice. And so this is actually a good solution when you can use it. Okay, so now we're basically almost there. Recall that what we wanted to was to compute the gradient of this ELBO, which is just an expectation with respect to Q of some arbitrary function which happens to depend on phi, which is a little bit annoying because before we had this R which was not depending on phi. Now the argument of the expectation also depends on phi, but you can kind of see that basically you can still use reparameterization. You still, just like before, as long as you know how to write down the sampling procedure in some kind of, as a differentiable, in a differentiable way, then you just basically have the argument of the expectation that depends on phi in two ways, and then you just do basically chain rule would basically take autodiff will take care of the gradient for you. So that's actually not an issue. Essentially, you use the same machinery for this reward function, which now depends on phi, but essentially the same machinery goes through. And so, okay, now we know essentially how to do this. We know how to compute the gradients. The only other annoying piece is that we have one variational parameter per data point. And so it would be kind of like expensive to have different variational parameters per data point, especially if you have a very large data set. And so the other missing piece is to have what's called as amortization, which basically means that we're not going to try to separately optimize over all these phis. Instead, we're going to have a single set of parameters, which is going to be another neural network. It's going to be the encoder of the VAE, which we're going to denote as f lambda. And this function is going to try to guess a good choice of variational parameters. So it's going to try to somehow do regression on this mapping between xi and the optimal variational parameters. It's going to try to guess what's a good way of approximating the posterior for the ith data point. And this is much more scalable because we have a fixed number of parameters now that we're trying to optimize. We have the theta and we have the encoder. And so again, so if let's say the Qs are Gaussians, instead of having one different mean vector per data point, you have a single neural network that will try to guess what's the mean of the Gaussian as a function of x, as a function of the data point, the observed values that you see in each data point. And now we approximate this posterior distribution given that the observed value is for the ith data point using this distribution. So we take xi, we pass it through this neural network that will guess the variational parameters, and then that's going to be the Q that we use in the ELBO. And the same kind of like gradient computation goes through as long as the as long as reparameterization works. You can see that sort of like the same machinery applies here.
We are clearly like losing a bit of like our ability to model the like data set by doing this. So is it worth to do this trade-off? Like, what if we just trained on like 100 examples with like a single phi for each rather than doing this? Like, what's the trade-off there?
The trade-off in that case, like you're going to get a better, I mean, to the extent that you can do the optimization well, because it's non-convex, so weird things could happen. But to the extent that you can optimize, you would get a better average log likelihood. So it's going to be more expensive because you have more variational parameters to optimize over. You're also going to give up on the fact that if I give you a new test data point and you want to evaluate the likelihood of that test data point, you would have to solve an optimization problem and to try to find variational parameters for that data point. If you have this neural network that is already trained to give good variational parameters, you have no cost. So it's all amortized. So it's kind of like, it's called amortized because essentially there is a neural network that is amortizing the cost of solving this optimization problem over variational parameters. And the problem of solving the optimization problem and give you the optimal variational parameters is kind of like amortized by a single feed-forward pass through this neural network.
If you are learning to separate VAEs, how would that generalize to a new data point anyway? You don't know the phi for data.
So it would generalize in the sense that you would have a P and you could try to evaluate, you could try to then, it defines a valid likelihood on any X. It might, optimizing through an encoder, might have a regularization effect in the sense that it's constraining P because you're jointly optimizing P and Q. So you could say that, okay, you're optimizing phi to try to make the approximate posterior close to the true posterior, but you're also optimizing the true posterior to be close to one that you can approximate with your little neural network. And so it has a regularization effect over the kind of generative model that you learn, because it has to be a generative model on which you can do inference relatively well using this single neural network that we have here. And so as you said, that might help you in terms of log likelihood on a new data point, because the model is more constrained, and so it might perform well. It prevents overfitting to some extent.
I see. But I guess like let's say you have 100 files that you've learned. For the test data point, do you learn a new file altogether, or you try to figure out which of the 100 files you already have best represented in this?
You could do both. If you wanted to get the best approximation to the likelihood on a new test data point, you would optimize a new file, and that would give you a valid, the best lower bound on the elbow for that data point. That would be the best. The marginal likelihood is defined regardless of how you choose the phi's, and so the phi is just a computational thing that you need in order to evaluate likelihoods. But if you just care about generation, you don't even need the phi's.
How many phi's would be sufficient to train a good parametric function?
How many phi's in practice? What you would do is you would have a single neural network that would essentially guess the optimal phi's as a function of the data points. And these neural networks are typically relatively shallow.
So you wouldn't need that many phi's to train that network?
You don't actually ever get the phi's. So what you do is you just optimize the elbow as a function of these, let's say, lambda parameters here. And so you just
Oh, I see.
And so you never actually compute these phi stars. You just restrict yourselves to the phi's that can be produced by this single neural network.
But we need to set like the dimensions of phi to be a hyperparameters.
Yeah, so the dimension of phi and the family that you choose, is it a Gaussian, is it a like whatever variational family, that's a choice, the modeling choice. So yeah. Yeah.
So now do we train lambda, phi, and theta jointly all at the same time?
So in this setting, I guess, I don't know if I have it here, but essentially you would not, you wouldn't even have the phi's, you would just have the theta and the lambda, and then everything. Yeah. And so let's see, what do I have here? Yeah, so essentially, again, this is saying what we were discussing before, that for different data points, there is going to be different optimal variational parameters, and then you have this single map that will take xi as an input and will output a good choice of variational parameters for that xi that you're going to use to infer the latent variables for that data point. So there is not even going to be any phi's anymore. There's going to be a single neural network f lambda that does the work for you. And in the VAE language, that's often denoted q phi of z given x, meaning that the choice of variational distribution that you use is a function of x and phi, and the relationship is determined by this neural network, which is going to be the encoder in the VAE that predicts the parameters of this variational distribution over the latent variables, given what you know, given the x variables. So it's the same machinery, except that there is less trainable parameters because there's a single neural network that will describe all these variational distributions that in general should be different, but just for computational efficiency reasons, you restrict yourself to things that can be described that way. And then basically that's how you actually do things. Then you have exactly the elbow that we had before, which depends on the parameters of the decoder and the encoder, phi. So phi here now denotes the parameters of the separate inference neural network that takes x as an input and produces the variational posterior q for that x. And then everything is just optimized as a function of theta and phi through gradient ascent. So you initialize the decoder and the encoder somehow. And then what you would do is you would randomly sample a data point. Then there is going to be a corresponding elbow for that data point. And what you can try to do is you can try to figure out how should you adjust the theta, the decoder, and the encoder to maximize the elbow for that particular data point. And this expression is just like what we had before, except that the variational parameters are produced through this neural network, which is the encoder. And you can just backprop through that additional neural network to figure out what this gradient should be. How should you adjust the gradients of the encoder so that you produce variational parameters for the ith data point that perform well with respect to the elbow. And you can still use the reparameterization trick as long as Q is a Gaussian. Everything sort of works, and then you just take steps. And in this version, which is the version that people use in practice, you jointly optimize theta and phi at the same time. So you try to keep them in sync so that, because we know that they are related to each other, we know that phi should track the true conditional distribution of z given x given the current choice of theta. And so as you update theta, you might as well update phi and vice versa. And so it makes sense to just compute a single gradient over both and optimize kind of like both optimization variables at the same time. And how to compute gradients, again, sort of like, let's say, reparameterization trick as before. And I think we're out of time, but you can kind of see now the autoencoder perspective. Q is the encoder, takes an image, let's say an input, and it maps it to a mean and a standard deviation, which are the parameters of the approximate posterior at that or that x. And then the decoder takes a z variable and then maps it to an x, and that's the other neural network. And you can kind of start to see how this has a autoencoder flavor. And in fact, what we'll see is that the elbow can be interpreted as an autoencoding objective with some sort of kind of regularization over the kind of latents that you produce through an autoencoder. And so that's why it's called a variational autoencoder, because it's essentially, there is an encoder, which is the variational posterior, and there is a decoder, and they work together by optimizing the elbow, and optimizing the elbow is essentially a regularized type of autoencoding objective. But we'll see it next time.